I guess we can go ahead and start the class just 1 minute early. Your exam 2 is graded. If you haven't picked it up, it's right here. You can pick it up and check it out. I assume you saw my email. We did much better than the exam 1, and which is a very good news to me. If you couldn't do well on this exam, don't worry about it. I mean, you just have to. I'm gonna use your final exams grade for your grade. That's the end of it, right? If you didn't do well, this extends to everyone. Let's say you have received a good grade, 82, but you got the 91 on your final exam, right? I'm not gonna penalize you because you did get a B on one exam and got an A on the other one. You will get an A out of the course, right? So this offer extends to everyone, not just people who did poorly on their exams. So I guess that's an incentive to do better. That's an incentive to do better on your final exam. And do we have any questions about the exam? We will go over the exam today. But do we have any questions about how the exam was conducted or the number of questions? Yes, yes. For the final? Yes, yes. Yeah. Yeah, so we will, for today, we will go over the exam 2 today. And we will talk about how the final exam is going to be structured, how the final exam, how the structure of the final exam is. I will actually give you the date of the final exam, which I have to look up. And yeah, I'm thinking of making some changes to the final exam just to make sure. But if there is no questions, we can go ahead and start. This doesn't come on. Let me just use my laptop for a second. Final exams. So for our class, the final exam is going to be on May 4th, which is a Tuesday at 4 p.m. So Tuesday, I will also send an email. Tuesday, May 4th. At 4 p.m. Okay, do you see this color? Let's see, let me use a yellow color. Okay, and your exam is going to be 2.5 hours. For those of you who have registered for that's SDRC, you will get more than this. You will get 1 hour and 15 minutes extra, which is going to be 3 hours and 45 minutes. 3 hours and 45 minutes. And we will have 8 conceptual questions, 8 to 10. This is a very long exam, final exam. And 6, let's call them numerical problems that you need to find an answer for. So essentially, the number of questions is going to be very close to the first exam. I really expect you to be able to finish this in less than 2 hours. So you shouldn't really need to have the full 2.5 hours. But I assume the amount of time you had for the second exam was enough. So taking that into account, you are not going to need more than 2 hours to answer all of the problems on the final exam. Okay. And there were a lot of people who they were struggled with the problem 6, which we are going to talk about on exam 2, which was from chapter 5. Chapter 5, yeah. So since this was the case, what I'm going to do is that I'm not going to include chapter 6, maybe just one conceptual question. And that conceptual question we'll talk about in the next lecture. So I will give you what I'm going to ask you from chapter 6, and you will be asked that in the final exam, right? That's good, though. Because there's only 2 things that I want you to take out of chapter 6, not more than that. So, and no one really covers chapter 6, so we are already doing extra. So chapter 5 will be included in the final exam. Okay. Essentially, what I mean is that a question that is very similar to the problem 5, problem 6, that was problem 6, right? Yeah, problem 6 of your exam. A question that is very similar to it will be included in your final exam. And problem 6 on the exam was actually an example we solved in class. It was in your lecture notes as well. Well, we will go over it. And also, there were also a couple of other people who struggled with, what was it? That was the last problem, problem 7. So, which was from chapter 7. Problem 7. And because of that, I will also include chapter 7 in your final exam. So your final exam will be chapters 1, final exam, chapters 1 through 3, then chapter 4, not chapter chapter 5, and chapter 7 and 8. So essentially, I'm one question from chapter 6 that you will know what the question is. So that's, I guess we can think of that as a kind of a help for your final exam. Essentially, what that means is that the only chapter that is not going to be included in your final exam is going to be chapter 4, right? Is there any questions about it? The number of problems, 6, 8 to 10 conceptual questions. And I will provide a final exam guide, especially for the conceptual parts. You already have a guide for the conceptual questions from chapter 4, 5, and 7. I will add chapters 1 through 3 and chapter 8 to it. Also, the one question from chapter 6 will be included in your exam guide as well. I will print it, bring it to class. We will have enough handouts to give you. I will also upload it on Blackboard. So the conceptual questions, as long as you know how to answer those, you should be fine. And I guess I should have mentioned this in class. I didn't want you to include the answers to the conceptual problems in your equation sheets. But since I didn't mention it in class, a couple of you asked it just before the exam, I didn't want to create more anxiety than necessary. So I just told everyone to bring it with your equation sheet. And since we did that for the second exam, we're going to do the same for your final exam. So you can include the answer to the conceptual problems in your equation sheet, right? And I mean, the conceptual problems will be about the concepts that you will see on your exam guide, but the text of the question may differ. So you should just have to make sure you understand what these means. Just do not copy and paste, okay? What else? I guess that's it, right? Do we have any questions? And again, if you do well, or let me put it this way. If you, let me put it this way. I am going to drop one of your exams. One of your exams, okay? So that's for sure. And this will apply to everyone, right? Let's say you have just a random, let's say you have a 70, a 90, and a 92. I'm going to replace that 70 with the 92 you have, with your highest grade, right? So hopefully you can get an A out of the course. But there are some people who didn't do well on both of the exam 1 and exam 2. Those of you who could not do well on both exams, if you get an A on your final exam, we can think of a way to help you for the other two problems. So for the other two exams. I don't know if that makes sense or not. Well, let's say you have failed both exams. Failed the other two exams, exam 1 and exam 2. But you get a 91 on the final exam. Your grade out of the course, if you have submitted all of the homework, should be around like D plus, right? Somewhere in that ballpark. But I will give you a B. Or if you get a 98 out of the final exam, I will give you a B plus. Not an A, because it's going to be unfair to the people who are going to receive an A on their own, but a B or a B plus. Does this make sense? Which I think is a pretty good deal. And also, we have had a couple of bonus point opportunities. They are still valid if you go, especially in the earlier lectures. If you go back to the earlier lectures, watch them, submit the bonus point, you will get the bonus, right? That's also an opportunity. And yeah, I guess that's it. Is there any questions about the grades or the final exam? Okay. So let's go to the exam 2. Let's talk about the exam 2. And we'll go from there. Also, the last thing, if you do not really feel good about your grade for whatever reason, say your grade is a failing grade, or you expect to get an A, but you're getting a C, you should definitely talk to me. Like sending me an email is definitely not harmful, right? But so don't come to me after the class and tell me what should I do to get a better grade, right? After the final exam, after everything is said and done, right? It doesn't work this way. You should definitely reach out to me if you want to do something, right? We can assign you a project. We can do something, right? I can give you more homework problems. These are all possible. But if you reach out to me before everything is said and done. Well, we did definitely much better on this exam. That's for sure. Okay, so Let's get to the exam 2. All of the exam problems were either from the homework, except for the last one, I think. Yeah, the problem number 5, 1 through 4, we actually had all of them on your conceptual problem part. And problem number 5, we solved in class just with a different U and V. Problem number 6 was an example. And problem number 7 was actually we solved in class. A problem that was very similar to it. Let's just start with problem number 1, which most of you got right. This is the problem number 1. This is the text. Define streamlines, streak lines, pass lines. And I'm going to ask you to, I'm going to give you a chance to answer my questions, these questions. Whoever volunteers will get a bonus point. Right? I guess if you have gotten the answer right, the only thing you really need to do is to read from your answer. And these bonus points are 0.5% of your final grade. So, number 1, define streamlines, streak lines, pass lines. When are they the same? What is the equation of a streamline? Okay, a streamline is a line that is tangent to the velocity vector. Exactly. Okay, what else? Streak lines consist of all particles that have passed through a common point. Exactly. Exactly. Okay, exactly. V over U, exactly. So, Mary Jane, right? Yeah. As Mary Jane put it, streamlines are the lines that are tangent to your velocity vector at any point. Streak lines consist of all the particles that have passed through this specific point in the flow, right? And pass lines is a path a particle takes to get from point A to point B, right? They are all exactly the same when the flow is at a steady state condition, which essentially means that the changes with respect to time are zero. The temporal derivatives are all 0. And the equation of a streamline, this line, is dy dx is equals to v divided by u. Okay. Second one. Now, for this problem, the problems that involve an equation or a solution, as long as you give me the correct methodology, you will get the bonus point, right? If you want to volunteer. Second one, write down the Reynolds transport theorem equation. Explain what it does. If you were to use the Reynolds transport theorem to derive the momentum equation, what would the extensive property and the intensive property for that purpose be? Do you have any takers? No? That's right. So Reynolds transport equation. Reynolds transport equation was this: the changes of extensive property of a system over time, that's the capital B, right, is equals to the changes of that intensive property over a control volume over time plus the net flow out or into the surfaces of that control volume. for the intensive property again. Right? This was the main equation. So again, let's say you have a control volume and you have a system that is passing through this control volume, right, over time. Let's say at time 0, the system exactly lays on top of the control volume. At time t1, it has moved out a bit, a little bit. So how much of this property B we have inside the control volume at time t1? This much, right? How much has moved out of the surfaces? This much. How much has changed inside this system of that, for how much that extensive property has changed inside the system? Well, we can't tell from the figure, but it can change, right? That's the idea. So what it does, it relates the changes of an extensive property of a system to the changes of an intensive property inside the control volume plus the net flux out or into that control volume, out of or into that control volume. Okay, 3 different sections. Okay. And if you were to use the Reynolds transport theorem to derive the momentum equation, so if you want to derive the momentum equation, your extensive property is linear momentum. What is linear momentum? mv, mass multiplied by velocity. And your intensive property, we define the intensive property as B divided by m, which means that you are going to get only the velocity. And for that purpose, we actually can write the momentum equation to be this. dmv dt is equals to partial t of control volume, rho v dv, and this v is volume, plus the control surface integral of rho v v and dA. Is there any questions? No. Okay. Next question. Define control volume and system. What are the differences?
The CV is the control volume, and it's the set boundary through which the fluid flows.
Okay.
And then the system is the collection of matter with its identity, and it can move, flow, and interact with it.
Okay. Exactly. Thank you. Cooper, right? So, number 3. As Cooper mentioned, control volume is actually an arbitrary selection in a space, right? Then we can have mass flow out of its boundaries or mass flow inside its boundaries. The only thing that is very important about control volume is that its volume has to stay the same. Volume is constant. We don't have any restrictions about its shape. So its shape can also change, right? It can move, if you recall, we actually had a couple of discussions about the moving control volume. But the only restriction is that its volume has to stay constant. So definition is a selection in a space, out of which boundaries you can have mass in and mass out. But a system, it's also a selection in a space, an arbitrary selection, but you're choosing a set number of particles. What does this mean? It essentially means that there won't be any mass going out or into the system. Its mass has to remain constant, right? So two selections inside your fluid. The difference between the two is that one of them can has mass flow in or out. The other one cannot have mass flow or in or out. One of them has to have a constant volume. The other one doesn't have to have a constant volume. Like for a case of compressible gas, right? Think of a cylinder in a car, right? Think of a piston in a car that is moving into a cylinder. You are compressing the gas. It's a system. There is no gas going out yet before the combustion, right? So that's a system. We are not losing any mass, but your volume is changing. Okay. Number 4. We actually had a lot of people who struggled for this question as well. What does the moment of momentum, or what does the moment of linear momentum represent? And write down the equation for it. Do we have any takers here? Yes, Cooper.
The tendency of an object to keep moving. It represents inertia.
Inertia. The moment of a momentum. Right? Let me ask you this question first. How do you take moment of something? Anything. Moment of a force. Like moment, regular moment is defined as r, that distance multiplied by the force, right? So what is moment of the momentum, of linear momentum? That times mv, right? That's the linear momentum. Exactly. So what is this? Just angular momentum, right? This moment of momentum, and this was the, you didn't have to explain what it means. You just had to tell me that it is angular momentum, right? And if you have past dynamics, you definitely know that that's angular momentum. For angular momentum, we use h, and it's actually conserved. We have a conservation of angular momentum. But the question is, rather than the equation we had in class, where we actually use the Reynolds transport theorem to find an equation for the angular momentum, equation of angular momentum as well. Let me make sure. Cooper 2. So the only thing you really need to do, as long as you have that equation, just can say that's R divided by mv of a system dt is equals to, then we have the intensive property. Just have to take the m out for the intensive property. Partial t. Intensive property is going to be rho r. And keep in mind that this is a cross product between two vectors. It is not a simple multiplications. It really didn't matter. Oh, there were some of you who actually made that mistake. I didn't deduct any points for those people who made this mistake. But there were some of you who wrote r dot v, right? These two are essentially the same thing if you're dealing with a scalar, right? dot and cross. But since we are dealing with a vector, this is a cross product and is different from the dot product of two vectors. So just make sure you are clear on this. Thank you. So number 4. Number 5. We had the best results for number 5. Most of you were able to answer this one. Let's actually, let me clean this. Number 5, a two-dimensional velocity field is given by u equals to 1 plus y, and v is equals to 1 plus x squared. Okay. Determine the equation of a streamline that passes through the origin. Do you have any volunteers for this part? Just have to tell me what to do. Don't have to. No. Cooper again.
You use the v over u is equal to dy over dx.
Okay, dy dx. Exactly. Thank you. It's equal to v over u. We have v, we have u. Plug that in, right? And what is v? 1 plus x squared divided by 1 plus y. We move x's to one side and all y's to the other side. So 1 plus y dy is equals to 1 plus x squared dx, right? Can we take the integral? Yes. Integral of this part is going to be y plus y squared over 2 equals to x plus x cubed over 3 plus a constant. How do we find the value of this constant? It is exactly, it is supposed to pass through origin, which is 0 and 0, right? So your x has to be 0, and it should give you a y of 0. Plug that in here, 0 plus 0, your y is 0 and 0 again, which means that your c is going to be equal to 0. Okay. Thank you. Part B. Find the stagnation points. Let's go with, he was quicker.
You just make u and v 0.
Exactly. So a stagnation point, all the components of velocity has to be 0, right? Not just the magnitude of it. So there were some of you who said the magnitude of velocity, which is a square root of u squared plus v squared, has to be 0. That is not wrong. It is true. Because this essentially means that these two have to be 0, because these are all positives, both of them, right? When you have the addition of two positive or 0 values is equal to 0, both of them have to be 0. But then you plugged in x and y, and for some of you that messed up the system. But the easier way is to set two components separately to 0. If you set u is equal to 0, 1 plus y will be 0. So your y is going to be -1 for u to be 0. But for v to be 0, 1 plus x squared has to be equal to 0, which means that x squared is equal to -1, or x is equal to a square root of -1, which is the imaginary number I, right? What does this mean? This means that this flow does not have a stagnation point, any stagnation point. Okay. And hold them, huh? 1. Thank you. So part C. Find the acceleration vector at 1 and 1. Mm-hmm. Okay. 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 Thank you. Thank you. Exactly. So for a of x is du dt, right? That's the material derivative or the total derivative of u with respect to time, which the general form of it is partial u partial t plus u partial x plus v partial u partial y plus w partial u partial z. This part is 0 because it's a two-dimensional flow. This part is also 0 because this u and v do not depend on time, right? So you're going to end up du dt, which is the component of acceleration in the x direction, is equals to u partial x plus v partial u partial y. The only thing we really need to do is to plug in these values and take their derivative. So a of x is going to be u is 1 plus y multiplied by partial u partial x. What is partial u partial x? 0, right? Does not depend on x, plus 1 plus x squared multiplied by partial u partial y. Take the derivative of this with respect to y. It will give you 1. Okay? So your a of x is going to be equal to 1 plus x squared. A of y, the general formula is similar to this. You can simplify to get to v partial u partial v partial x plus v partial y. This term goes to 0 because v does not depend on y. So you'll end up with u partial v partial x, which is 1 plus y multiplied by 2x. That's the derivative of v with respect to x. So 2x. That will be your a of ay. And we want that value at point 1 and 1. X equals to 1, y equals to 1. Plug that in. You are going to get 2 here. And you plug it in here, you're going to get 4. So a vector form representation is going to be axi plus ayj, which is 2I plus 4j, right? Okay. Any questions so far? Okay, let's get to the second one. Water flows through a horizontal 180 pipe bend as shown in the figure. We have the flow cross-sectional area. The question I have on mine is a little different than yours. This was a little harder on my notes. Just made it a bit easier before the exam. Okay. So water flows through a horizontal 180 degrees pipe bend as shown in the figure below. The flow cross-sectional area is constant at the value of 0.1 square feet through the bend. The magnitude of the flow velocity everywhere in the bend is actual and 50 feet per second. The absolute pressure at the entrance and the exit of the bend are 30 psia and 24 psia, respectively. You want to calculate the component of anchoring force required to hold the bend in place. Do we have any volunteers? No. Okay, let's think about it a little bit together, because this is something we actually solved in class. And at any point, if you volunteer, I guess you have one volunteer. One,
I
two.
started by solving for the mass flow rate.
Okay, what does that mean? What did you do?
I found the density using its specific weight, and then I plugged that into the equation for mass flow rate, rho AV.
So conservation of mass then, right? So m dot in equals to m dot out, right? But how did you want to get that? You will get the bonus point. Let me write the. You already have 4 bonuses. That's good. How did you want to get to force from there?
I think I did it wrong, but I tried solving for force by doing the mass flow rate times the velocity.
Okay, that's the momentum, right? That was the original idea there, right?
The way that I tried to solve for force was with the pressure that was given.
Okay.
Use a pressure over area is equal to force.
Okay.
Plug that in.
So what's your name again?
Colin?
Connor. Yeah. Yeah. What was your last name? Okay. So one thing that before you go further, one thing that's actually a very important note for everyone in the class is that pressure is force per unit area, right? So P is equals to force divided by area. So if you want to find the pressure force, you have to multiply pressure by area. Okay? Just have to make sure you don't make that mistake. I mean, if you have the units in your mind, that's especially in SI, it's newtons per meter square, right? So what did you do afterwards?
So then I used that on the other side of the mass flow rate conservation equation, because force is equal to mass. I'm having a brain fart.
Don't worry about it. Don't worry about it. No worry.
So I plugged that in with the other stuff that I had put in, which was, I think I did, what was it? Rho times the velocity times area
Okay.
for the first side, and I did the in and out, so I got a value for that on one side, and then on the other side I have the force, and then I solved for the force.
Yeah. So you were moving in the right directions, but there were a couple of hiccups in the way that made your final answer not completely right. Do you have any other one who wants to jump in and tell me what they did? It doesn't have to be the exactly correct way, just like this force thing, that's very important. A lot of you made this mistake, and it's very important that it was brought up, because I usually don't remember these. And we will talk about the equation you used as well, both of you. Do we have anyone else who wants to jump in? No? Okay, that's all right. So first thing, and this type of question will definitely show up on your final exam. That's 100%, right? Not the exact question, but the type of question. So this solution methodology is something you want to make sure you know, right? Okay, so you are told to find the components of anchoring force required to hold the bend. So you want to find a force. What is the first thing you do when you want to find a specific force? The first thing you do is to draw a free body diagram, right? Draw all of the forces. Okay. And a lot of people actually had problem here because they didn't draw all of the forces that are present here. So we have a very badly drawn. This is a horizontal pipe. And you are told that this is your coordinate system, y, z, and x. So we have an anchoring force in this direction, right? This direction doesn't really matter, but if you choose a wrong direction, you'll get a negative value for that force, which essentially means that you should have chosen a reverse direction, right? What are the other forces that are present here? We are given a pressure, right? And we know that pressure results in a pressure force, or pressure force results in some pressure, right? That's a clue for you that you definitely need to have a pressure force. We are given the pressure distribution. It's a uniform distribution. So we can simply find the pressure force as P multiplied by that area. We have the pressure in both inlet and outlet of the pipe. And we are also given the pressure. It is better, you are given the absolute pressure. It is better for you to, and you have to change that to gauge pressure, right, to be able to use it here. How do we change absolute pressure to gauge pressure? It's in, your values are in feet. So British system, just subtract 14.7 psi, right? That was the idea. So we have the free body diagram. That's the first thing. And your force, your sigma of forces is going to be, this is called section A. On your exam, this is called section 2. So it is going to be P1A1. That's the pressure force over there, right? And we have the positive direction of y here. So this is a positive force plus P2A2. That's another force that is present. And this is sigma F in the y direction, right? Minus your anchoring force. You can name it anything you want. I'm going to name it R of y. You can name it F, you can name it A, whatever you want to call it. Doesn't really matter. Okay. What about other directions? What are the forces in other directions? Do we have any other forces? We can definitely have a force. The z direction is this. We can have the weight force, right? By this, we are told that this is a horizontal pipe, and so that weight force is being circumvented somewhere else. So there is another force that is circumventing weight force, which means that we don't need to include this in any of the calculations to make it simpler. Is there any force in the x direction? We may have an anchoring force in the x direction, but since we don't have any other forces present, that anchoring force is going to be 0, right? So that's it. The only direction we really need to care for is the y direction. So we have sigma of F, right? But if you recall from the Newton's second law, sigma of F is equals to ma, right? For a solid, we are dealing with a fluid, which essentially means that we have to do total derivative of mv with respect to time. In a solid, this is exactly the same thing as ma, because if you assume your m is not changing, you can take m out of the derivative, and dv dt is your acceleration, right? But in a fluid, you can't just take m out of the integral. So, and this is for a system. Sigma of your forces is equal to total derivative of mv with respect to time, which is equals to this, right? This is another equation we have for d and v, for the linear momentum, right? This is d linear momentum dt, which gets us to the equation, the momentum equation, right? So the sigma of f, and you don't need to go through all of these calculations in an exam. I'm just trying to explain it to you so you understand better, right? Just can plug in the final equation. Is going to, so this sigma of f is equal to partial t of control volume rho v dv, which is the integral over all of the volume of the pipe, right? And how it changes with respect to time. But we are told that the velocity is a constant value of 50, right? That's it. We are not told of any changes that may happen with respect to time. So this term is already canceled. Okay. Plus whatever happening, whatever going out or coming in from the control surfaces, dA, right? So, and that is whatever going out or coming in from all of the surfaces. How many surfaces do we have on this pipe? We have 3 surfaces, right? One inlet, one outlet, and one the pipe, the surface, the circular, the cylindrical surface of the pipe, right? Is there anything going out of that cylindrical pipe surface? No. It's just a wall, right? So there are only 2 surfaces that are going to play a role here. So this integral is only being applied to these 2 surfaces. But let's see how we can simplify this. We are not told, but we are just given one value for density, which means that density doesn't change over this cross-sectional area, over this surface, right? This is an integral over a surface. Density doesn't change over that surface, so we can take it out. What can we say about the velocities? Velocity also doesn't change over that surface, so we can take it out. Okay. What about this term? This weird term. What does this mean? First of all, this is the velocity that is normal to your surface, right? So if the inlet surface was like this, right, and velocity fluid was coming in this direction, this would have been your vector v, but the velocity that is normal to that surface would have been the projectional velocity that is normal to the surface. Does this make sense? So this is going to be v dot n. What is that value for this surface? The your velocity is already normal to the surface, right? Which essentially means that this v dot n is actually just v, okay? So let's simplify that. Control surface, rho v dot n. Velocity is already normal to the surface, so we can just take the n. Let's remove the n from that discussion, dA. What if this wasn't the case? What if we had this situation? And this is also an example we have solved in the lecture notes. Then you had the theta. You should have given, I mean, if that was the case, I would have given you the theta, right, which is the angle between the velocity vector and the surface, right? And then this v dot n would have become v cosine of that theta, right? Does this make sense? Okay. So, but in this case, that's not the case. It's just going to be V. And we said none of these actually change with the area over that cross-sectional area, over this area, the inlet or the outlet. So this integral is going to be rho V squared integral of dA over your area, over that control surface. What is the solution to this integral? Just A, right? But we are taking this integral over all of the surfaces, not just one. So we have to take the integral for two surfaces. It's going to be rho V squared A out minus rho V squared A in. You may also ask, where did the negative sign come from? Right? Why aren't we adding those? That also goes back to the philosophy behind this V dot n. Right? For an outlet, for an inlet, this is the direction of velocity. But this normal vector, which is normal to the surface, is in this direction, right? So they are in different directions. They are the angle between them is 180 degrees, which means that this is going to be equal to negative V, right? And that is the reason behind this negative sign. But you don't need to, as long as you point out to the correct equation here. So if your velocities are normal to the surface, this will be your correct equation. If not, you just have to add a sine or cosine of alpha, depending on the projection of velocity, right, to this equation, right? And this has to be equal to your sigma f. Does this make sense? Okay. So let's plug in the values and see what we are going to get. We have the pressure. We have the pressure forces. Both of them are absolute pressure, so 30 minus 14.7. And that's PSI, right? That's pounds per square inch. But your area is given to you in a square feet. So you have to make that conversion. You have to convert the square inch to the square feet here. We have to have PSF. How do we make that conversion? How do we convert a square inch to a square feet? You have to multiply it by 144, right? So every 1 square feet is equals to 144 a square inch, right? Here, PSI is pounds per square inch, right? To convert it to pounds per square feet, we have to divide this by 144, right? 144 comes to the numerator. So we have to multiply it actually by 144 to get to the pounds per square feet. Okay. And that is multiplied by the area, which is, in this case, is 0.1. All of these are added together. So we did the same thing for the other one, 24 minus 14.7 multiplied by 144 multiplied by 0.1 minus your reaction force, your anchoring force, whatever you want to call it. And what was your name? So Connor, right? I don't want to forget the bonus points. And that is going to be equal to rho VA out minus rho VA in. Something you have to keep in mind here is a directional velocity vector, right? They are moving in opposite directions, right? So one of them, depending on where your positive value of the coordinate system is, one of them is already a negative sign, right? So we actually, at the end of the day, we actually have to add them, not subtract them. In this specific case, not every time. In this specific case. So on the other side, we are going to get density, rho v squared a plus rho v squared a. Velocities are the same, aren't they? Yes, they are. Density remains the same. Area is also the same. So 2 multiplied by rho v squared a. What is the density here? Density is, we have to calculate density as well. We are given gamma. We are given the gravitational force. So you can calculate the density as gamma divided by gravitational force. Do we have a calculator? 1.94. Slugs per cubic feet, right? So 2 times 1.94 times velocity squared times area, which is 0.1. We have everything here, right? So we should be able to calculate R of y. Do we have any questions? So this is the type of questions that will definitely 100% show up on your final exam. So make sure to learn this. Also, to make sure to learn understand this part as well. You had a couple of examples that velocity normal to the surface was not in the same direction as the velocity vector, right? So you had to include this sine or cosine. They were part of your homework. We actually solved one example in class as well. So make sure to go back and review those too. And the last question number 7. So we are told the pressure rise delta P across a pump can be expressed as delta P equals to a function of your diameter, your density, your angular velocity, rotation, speed, and your volumetric flow rate. Diameter of the pipe, density of the fluid, angular velocity, the rotation of the pump, and the volumetric flow rate, right? Where d is the impeller diameter, rho is the fluid density, omega is the rotational speed, q is the flow rate. First part is asking us to show how many dimensionless parameters are required to model this problem. Do we have any volunteers? Yes.
You have to find K, which is the number of parameters, which is 5, and then R, which is the number of dimensions. Yeah, dimensions. And if you use MLT, then you get 3, and you subtract 3 from 5, so there's 2 pies.
Exactly. What is it, Ansley?
Ansley Gray.
Yeah. Thank you. Okay, exactly. So the first thing you need to do is to count the number of parameters 1, 2, 3, 2, 5. 1, 2, 3, 4, 5. And then you have to find the number of primary dimensions that are present in this problem. How do we do that? The first thing is to find the dimensions. Delta P, let's do MLT as the primary dimension, right? Your delta P is newtons per meters squared. Newtons itself is kilograms meters per second squared divided by meters squared. So you're going to get kilograms per meters second squared, right? That's for your pressure, delta P in MLT. If you were to use FLT, it would have been just newtons per meter squared. So that's one dimension, which is mass divided by length times a squared, right? That's one dimension. Diameter is meters, so just length. Density is kilograms per cubic meters, right? So mass L to the 3. And omega, or the rotation speed, is rotations per minutes or per second, or radians per minute or second. Radians or degrees is not a dimension, right? So your dimension here is actually 1 per second, right, for angular speed. That's actually something a lot of people struggle. So angular speed, that's per second. That's going to be your dimension. And the last one is the volumetric flow rate, right? How much volume is passing through a cross section over time, which is cubic meters per second, or cubic feet per second, depending on the system. So cubic meters, that's length cubed per second. So how many primary dimensions are present? Mass is present twice. Length is present everywhere. Not here, but time is also present a lot of it. So all 3 primary dimensions that we are concerned with are present, right? I think if you remember that I mentioned that there are actually 7 total primary dimensions, but in fluid mechanics, we don't really care about the other 4. So 3 primary dimensions are present, and the number of dimensionless parameters is going to be able to model. We have to calculate to be able to model this problem is going to be k minus r, which is 2. Okay. Part B. How many repeating and non-repeating variables do we need to model this?
Because it's 2 pi terms, you just need 2 non-repeating and 3 repeating.
Exactly. So what is repeating and non-repeating parameters? What are those? The non-repeating parameters are the parameters that are not going to be repeated in your pies, or the parameters that are very important to you, right? How do we choose those parameters? It's just at random, right? And not really at random, but you can use them at random. We have 2 pies, which means that we have 2 non-repeating parameters, right? And since we have 5 total parameters, the rest of them are going to be repeating parameters, right? So 2 non-repeating parameters, 3 repeating parameters. And part C. Find one of these dimensionless parameters using the Buckingham-Pi theorem. Okay. Do we have any takers? That's all right. So let's choose the two non-repeating variables. I'm going to choose delta P and Q. So we're going to have delta P for pi 1 and Q for pi 2. What does it mean for the other ones? The other ones can be, they don't have to be presented in all of the pi's, but they can be present, right? So we can get rho to the power A1 for the pi 1, omega to the power B1 for the pi 1, and what's the last one? Diameter to the power C1 for the pi 1. For pi 2, same thing. The only difference is going to be your power. And all of these dimensions have to cancel each other to give you a dimensionless parameter, right? That's the idea here. So let's actually do the pi 1 first. The dimension here on the left-hand side is 1. On the right-hand side, we have for delta P, we have mass divided by length, T squared. For your density, we have mass divided by cubic length to the power A1. For your omega, 1 divided by time to the power B1. And for your diameter, we have length to the power C1. These type of problems, you just have to keep in mind that you may get a different solutions based on your choice of non-repeating parameter, right? So as long as you have the correct procedure, as long as you have done the correct calculation, you will get a credit for your whatever you have done. So what should we do, right? You want to make sure that all of these cancel each other out. How do they cancel each other out? The first step is to combine or write them in an orderly way. That's the best way I could put it. So one is, let's get all the m's together. We have m to the power 1 plus m to the power a1. And something that you just have to keep in mind that m to the power 1 multiplied by m to the power a1 is m to the power 1 plus a1, right? What else? We don't have any m's anymore, right? Not in here. Multiplied by, let's do the length for the next one. L to the power -1 plus or minus -3 a1 plus c1. And then let's have time. We are going to have -2 and -b1. Okay. For the left-hand side and right-hand side to be equal, or to give us 1, all of these powers have to be 0, right? Which is going to give us a system of equations and unknowns. Let's write all of these down. One plus a1 equals to 0. -1 minus 3 a1 plus c1 equals to 0. And 2 minus 2b1 is equals to 0. This tells you a1 is equals to -1. This tells you b1 is -2. And this tells you c1 is -1, +3, -2, right? So what does this mean for pi 1? We have a1, b1, and c1. Plug that in. Delta p rho to the power a1. What is the value of a1? -1. Then omega to the power b2, that's -2. And d to the power c2, which is again -2. So pi 1 is going to be equal to delta p divided by rho omega squared d squared. And that's it. You would have gotten a bonus point if you did the same analysis and gave me a pi 2, which I assume will be there for your final exam as well. So if I ask you to the pi theorem, one of the pi calculations will be necessary. The other one will be just bonus. And I think 4 or 5 of you actually got this bonus, which is a very good statistics. Is there any questions? So next, I mean, on Thursday, Thursday is the last lecture. If you want me to focus on something, please send me an email. I will focus on it. And the last 15 minutes of the lecture, or last 10 minutes of the lecture, will be dedicated to filling your evaluation, like submitting the evaluation of the course. I will leave the class. You can just have your laptop, or if you use your phone to do the evaluation. And there are a couple of people who have already sent me their receipts of the evaluation submission. Whoever does that will get a bonus point. And if you submit the evaluation and don't send me the email, you're essentially missing out on a free bonus, right? Okay. Is there any questions? No? Okay. Have a good day. And happy 420. Right?